Hello everyone and welcome to a new episode of All Things IDA. In today's episode, we're going to learn about different ways we can patch with IDA. We're going to be patching the input database and then applying this back to the input file. We'll show how to do this using IDA's UI, using IDAPython programmatically. And finally, we'll show you how to apply the changes back on disk. And as a simple bonus, we're gonna do the other way around. Supposedly we patched the input file externally, how to bring it back into the database. Okay, so let's get started. Okay, so let's start with the UI, how to use IDA's UI to patch. The first method we can use to patch is through basic byte manipulation. So we're gonna, in here in the IDA view, we cannot do much really to directly edit and patch. Instead, we can assemble and show you that afterwards. But for now, to patch, just simply patching like we would with a hex editor, we'll have to open a hex window. So go open subviews and we choose a hex view or hex dump. And this is basically our code. And now we can simply start patching. So what I'm going to do is just maybe patch a string just to show you. So I'm gonna find the help string here, see where it is, and let's synchronize hex view with IDA view. So like this, we have the same view on both sides. So right click, synchronize with IDA view. So this is the string. Now to patch at hex level, basically, we just press F2 or right click and edit. So the F2 is the shortcut. So once we press F2, and now we're in edit mode. So here now we can start either typing hex characters here. So for example, 45, 45, 45, for example, and then we press F2 to apply the patch. So pressing F2 again, right click, and F2 again, it applies the patch. Let me edit it again. So I'm gonna put the cursor this time, not on the hex view, but on the text view, the ASCII view out of it. So we can either patch by typing hex characters or by typing a regular strings here. So here, let's say this is a help screen. Then, for example, we can switch back here and put like 0A, switch back here, type what we want, maybe even null terminate the string quickly, press F2, apply the changes, go back here, refresh, and we have the apply changes. Let's remake the string here because I was a bit confused. And go back to the decompiler. We should now be able to see a shorter string. Now, how do we see what we have patched so far? And this is very important. We can go to the view, subviews, and we open the patched bytes window. So Ctrl-Alt-P. And here we have a list of all the stuff we have patched already. The addresses, the lengths of the patch. If you start patching at a certain address all the way to the other address, IDA will not create individual entries for consecutive addresses. Instead, it will, if they are consecutive, it just say we started patching here up to a certain size, and these were the original bytes, and these are the patched bytes. Now we can get all this information as well programmatically. But for now, we're using the UI. So these are all the patches that we have done so far. We can always revert the patches using the regular undo. So we can always undo, undo, undo. Let's open here the undo history. And basically, when we started to apply changes, these are the undo items we want to undo really. So Ctrl-Z is okay, but it's gonna let us basically undo other stuff. So a better way, if we have made other actions after the patching, a better way to revert patches is just to open the patch byte window and delete, right click and say delete, which maps to revert. So if I select everything here and delete, we should have reverted everything. All the patches are gone, so going back here, we can revert it, recreate it, refresh, and we're back to the original case. So this is how we can patch using the hex editor, how we can see the patched bytes, how we revert the patch bytes. So that's patching on hex level. Now the other way we can patch on a code level, a more technical term to it is assembling. So instead of saying we're gonna patch the code, we're gonna say we're gonna assemble new code instead. So if we don't know the actual hex opcodes, we can just write the mnemonics, the regular assembly syntax. So let's simply invoke now the assemble functionality. So we can go to the edit menu, patch program, and here we have assemble functionality. Pops up a built-in assemble function. This is coming from the processor module. Now this is a very primitive assembler. And we'll see behind the scenes where it comes from, how we can extend it, and so on. But once we invoke the assemble functionality, we get the dialog where we can assemble things. So here I can say, for example, move EAX123. And here we go. This is the assembled bytes. And if I open the patched bytes window, we should see as well a patch entry. So here we go. We patched the code, we put the new instruction, it was a push, and now it's a move 123. So that's the assemble. Now you notice assemble is not very complicated. It's a limited assembler. So let's see where this assembler comes from and if it's extensible or not. If we go to the SDK, we have in the processor module header file idp.hpp. This is where we have the processor definition and the processor notification events. These are events that the processor module should answer. We have covered like instruction decoding in the past, and instruction decoding or instruction analysis, the analyze event, is responsible for decoding. And similarly, we have an event called EVAssemble. If that event is implemented in the current processor module, then you're supposed to return the assembled bytes. So the user passes a line to assemble, asks if it's 32 bits or not, passes the EA, code segment instruction pointer. These help in when we're assembling instruction pointer relative instructions. Anything relative, we need to give the assemble instruction that context. Where are we assembling from? Because that will affect the instruction encoding. So that's our output buffer. These are all to give context to the assemble function and the line to assemble. We send that event. The processor module behind the scenes takes that line string and tries to assemble it. And the limitation we're facing with the IDA built-in assembler is because it's just primitive, it's not hooked to a better assembler. It works for simple instructions to assemble, but it's not as powerful. We can use an alternative. We're going to talk about Keystone and Keypatch in a second. But this is where the assemble comes from. Additionally, we can programmatically call the assemble. So when we went here to the assemble menu and put things, we also have an exposed functionality we can use from IDAPython where it will generate the event, send it to the processor module, and either give us back the assembled bytes or directly patches them to the database. So we have two functions. The first function is called assemble line. It is implemented in the idp.I, which is basically the Swig file that is used when we're building IDAPython. So here what we're doing really, in the assemble line implementation, which is going to be exposed to us into IDAPython, we are using the assemble methods provided to us, which behind the scenes is a simple inline function that simply sends a message to the processor module, sends the EVAssemble event. So it passes everything the user passes, and simply returns the assembled bytes. So assemble line will give you the assembled bytes and you can do whatever you want with them. So here, for example, let's invoke it. So here I have, let's say, assemble line, IDAPI.assemble line. We have to give it, let's see the documentation real quick. Explain it. So basically, assemble line, as we said, EACSIP. If we're working with a linear program, then the CS is just 0, since it's linear. IP and EA is going to be the same. Use 32 or not, so that's already some kind of a limitation in the interface where it doesn't mention 64 bits and so on. But since now we're working with 32-bit program, we're good. So assemble line, EA is going to be here, code segment 0, IP is also the same as EA, use 32, and we're going to assemble. It's not going to work for this RAX. We're going to fix it here, just assemble move AX1. And this is the assembly bytes of move AX1. We can take this, do whatever we want with it. It did not patch it at the EA. So now let's use the assemble method, which is almost similar, except that it patches. So here, it says assemble instruction to a string. That's it. But the assemble will also patch it. So this is the difference between the two. So here, let's just type assemble and show you what we're talking about. So assemble takes same arguments, so EA, CS, IP, U32, and the line. But the difference is assemble into the database. So we don't have to patch it. In the previous case, assemble line will get the bytes, we then patch the bytes back. Here, it's a single call. So let's just call this. We should see here at the current screen address, we should see a move AX1. Here we go, we patched it. If we open the patch window, same story, we have the patch that we just applied. So this covers the built-in functionality about patching and in the hex view and assembling. Now let's talk about more advanced cases, different, more powerful assemblers and so on. So for this, I'm gonna be mentioning the Keystone engine. It's from the same author that did Capstone and Quilling and so on. The Keystone engine we can use in C++ and Python and all the other wrappers. There are different languages supports and so on. So the first thing is we need to install it. So just pip install Keystone engine. So here, this is what I did. I simply installed it, got installed, and I'm good to go. Now I can use it. How do I use it? I can use it programmatically. So it's very, very simple interface. All we have to do really is, the first thing is simply, we have to initialize the Keystone engine with the proper architecture. So here we're gonna say, we're gonna use the x86 processor module in 32-bit mode, and that's it basically. This is what we want to assemble. So we can assemble one instruction at a time, or we can put semicolon. So all we have to do is just create a Keystone object and then call the assemble method. So let's try it out. Let's take this, go back to IDA here. Again, now the assemble just assembles. It's not gonna put anything, but this is much, much more powerful than the built-in IDA assembler. So if we want to programmatically take it to the next level, instead of using the basic assemble in IDA, we can use a third-party framework. So let's just create the object and explore manually. So just this, and first, let's also get this one here. All right, so we have Keystone, we create an instance, let's run it, it succeeded. Now we can say, for example, ks.assemble, and we see, for example, it has a bunch of methods, but the most important method really is just like assemble. It has a symbol resolver, very useful. It's an advanced feature. We can implement that callback to help it resolve certain symbols. We can hook it up with IDA symbol resolution. So if we type symbolic names in the assemble, then Keystone will go consult the handler, say, hey, the user assembled something that contains symbolic names, like an address, label name, function name. How do I resolve it? Goes back to IDA, hey, given a name, give me the EA, gets back the EA. Keystone knows how to assemble based on that address, especially if it's relative to the instruction pointer or and so on. So here we can assemble. We can say ks.asm, for example, call this one. Let's say call this instruction, and we're assembling it. For example, if we want to call free instead of call this, so we're gonna assemble this address. We're gonna call, instead of mixer this, we're gonna call this function. And the address is this. We can see actually the encoding, the relative call 07, which basically is 7 bytes after that instruction. So really, if we go +7 here, we did reach that destination. Now, on top of Keystone, there's another IDA plugin that makes it easier to assemble graphics. And that plugin is called Keypatch. We can also download it from the Keystone repository and drop it in the plugins folder. So here I put Keypatch, and it integrates into IDA. It has a bunch of functionalities. Now, this plugin is older than when IDA had undo functionality. So that plugin was also exposing its own undo. It's not needed anymore. IDA has built-in undo. So what we care about is just the assemble functionality. So Control-Alt-K. We can now say edit, and here we have the Keypatch plugin installed some menus programmatically and expose the patching functionality. Let's say we want to change this to call this address here. So Control-Alt-K, and we can just say call. And the moment we put a proper assemblable line, we get to see the encoding, get to see the instruction size. If we are assembling and the output is smaller than what was, then we'll have some loose instructions that are no longer valid. So here we have an option. If the assembled instruction is smaller than the one we actually patched, then fill in the rest with an op, and that's very useful. So we can assemble, and then it will patch once we agree. And here we go, here it patched. Now we called that address that I wanted to call. I'm gonna undo. And the nice thing about Keypatch as well is we can assemble progressively, in the sense that once I invoke it here, I can just press enter continuously and it advances to the next addresses. So here I'm gonna say I'm gonna XOR EDX, for example, press enter. I patched this. Now it moved to the next line. Now it's gonna try, is moving until I cancel. So here, let's say I wanna move ESI 1, 2, 3. Mul EDX, I'm gonna replace it, let's say, with call. And here, let's say we're gonna call mixer get line info A. And that is the symbol resolver. So we did put something symbolic, but Keystone integrates with IDA through the sim handler, and it knows how to resolve that name. So in reality, we have a lot of flexibility. We can pass symbol names. We don't have to pass hard-coded addresses. Patch, and here we go, we have patched it. So this is Keystone, and the same story. If we open back the patch byte functionality, then we will still see the same things over and over. Now you notice in IDA, these are the patches. If we go to the edit menu, go back to the patch menu, we have a functionality called apply patches to input file. So this is one way to bring the changes to the input file. The older way existed a long time ago, before that functionality I just showed you. So the classical way is create a diff file. And like this, it creates a diff file with a common or known structure. Diff files have a known structures. First thing is like the description, and then the file name, and so on and so on. And then the list of before and physical file offset before and after. I'll show you the actual format of the diff file. So let's go to the file, produce, and let's export our patches so we can apply them if we want outside IDA. So here we go, patch diff, we created that file. If we show you that file, so this file here has a title. There's subtitle here, or empty line, the input file, physical file offset, original bytes, patched bytes, original byte, patched bytes. Now all you have to do is simply use a simple tool that knows how to interpret this and apply the patches. This is one way. File, edit. Let's now first apply it using IDA's functionality. You say, okay, what range you want me to take the patches basically from the patch log that IDA knows. What is the input file you want to patch? If you want to create a backup, IDA has that feature as well. And it can go the other way around basically. So instead of patching from that second column, these are the patched bytes. If we say restore original bytes, Internally, IDA, instead of using the patched byte, we use the original bytes to revert back. So let's just do the proper patching. We're not reverting anything. Okay. And here IDA went, opened the file, created the backup, applied the patches from IDA's functionality without going through a diff file. So here, let's just compare the two. Show here, for example, 31 became 33. So here is, this is the patched one, that's the original. That's the patched one, so here 32, and the original here is 33. So here is the original one, and here is the patched one. Now let's see how we can patch it through a diff file. So I'm gonna revert the backup, and now we already exported the diff file. So as we said, we just want a tool or a script that can apply this. So if you generate a diff file, send it to a colleague that doesn't have IDA, just have the input file and a diff file, we can use a simple script to apply these. And for that, I wrote a very simple script you can use. It's in useful scripts in my repo. It's called apply diff. So here in the Python folder, apply diff is a very simple diff file patcher that works with IDA. But the diff file is not just IDA format. As I said, any other diffing patching tools can generate diff files. So now let's invoke the patcher. So here I have the apply diff, and it wants -i the patch file and the output file. So -o, and we're gonna specify Wismo 32. So, and then we have another flag, which is force. Force will not verify the bytes. So here, when we patch, the patcher makes sure that before patching the original to the patched byte, we make sure that the original byte is really 33 or C9 and so on. But if we force, we're saying don't verify the input file before applying the patch. It's safe to have verification to know if you're overriding a previous patch that is not compatible with your new patch, for example. So for now, I don't think this will give us any errors because it is we are applying it on the original file, so the original bytes will match the patch, will match the input file. So the diff files is original bytes, and the physical files bytes will be matching. Therefore, no need to force patch. So let's try this out. And the same story like in IDA, it says like, hey, I applied this many patches and so on and so on. Now the difference, this tool does not create a backup. That's why I created the backup manually. And also let's compare. And the same story. So 33, 31, and the patched, as we said. So original bytes, patched bytes, and so on. So these are the methods we can patch in IDA. And this doesn't have to be just a 32-bit program or x86. It could be ARM or any other processor module. In fact, if we look at the Keypatch source code, it knows how to initialize the Keystone engine depending on the processor module that it queries from the IDA database, from the input database. So if you open a PowerPC 32 IDB file and you invoke Keypatch Ctrl-Alt-K, it will create a Keystone engine instance properly. So remember, when we create a Keystone engine, we have to specify a bunch of arguments like what is the processor module and what's the mode. And that's how the graphical plugin for IDA, the Keypatch, knows how to deal with this. So this is from going from IDA to the binary. Now let's see how we can do the other way around. Somebody gave us, we started with an exe file, we have the database, and then somebody gave us a patched exe. Now the size did not change, we simply patched certain things. How we can bring in things back again? So let's do that exercise. I'm gonna patch this help string externally and then bring it back to IDA. So if you're using your hex editor, I don't know many people that like to use Hiew as I do. I've been using it since at least 1995. If you're not using Hiew, now why did I mention this? Hiew is a bit more advanced. It understands virtual addresses. So here we can see the dots. These dots, that means the virtual address. Versus if we switch it to file offset, I got rid of the dots and we see all the physical offsets. So in Hiew, we can seek using physical offsets or virtual addresses. So here, for example, in IDA, we have that string. How do I really know where it is in the exe? I can search, I can seek, but to seek into the file here, we need to match it with IDA. So this is the virtual address. But what about the physical address? Actually, the physical address shows here in the local status bar, and this is the same, but the virtual address. So if we're using a basic hex editor, that's the address you want to seek to, the physical offset, 1B90. But if we're using Hiew, I can just press F5 to seek. Here, F5 is seeking. And I can type dot and put the virtual address as I see it in IDA. So dot 403.190. And here I am at the string. And now I can just patch using my hex editor. This is a test from patching with Hiew. I'm gonna save and exit. So let me verify my patch here. This is a test from patching with Hiew. Unfortunately, I patched on top of the patch, but fine, it doesn't matter. We want to see just the string that I just did. So now, you got that exe. So Wizmo has been patched externally. How can I nicely bring in all the patches from that exe into the database? So we can say file, load, and we have this option. Reload the input file. Now this will be valid or useful if we do have the input file. Remember, sometimes we might start with a database, maybe from a dump file, from a debugging session, by being built synthetically, programmatically, and so on and so on. So this is applicable when you start with a proper input file. So file, load, reload input file. It will be fast, and you'll see the changes shortly after it finishes. So here, reload. It says I have reloaded the file, and here we go. This is a test from patching with Hiew. Now, again, that did not inform the IDA kernel about the implications of the patch. So really, it might be an expensive operation to rerun the whole analysis and so on. But in fact, here, IDA did not destroy the whole item. It didn't know really what happened, that the item is smaller. So now here we terminate with 0, but after the patch, we put a 0, but before that, the string was like this, so IDA created an item that big. So in that case, it's a simple fix, really. We can just press A to let the kernel recreate a proper item and so on. So just pressing A to make a string, it will properly adjust it. But that's not a big deal, really. Instructions don't need these kind of things. Maybe we need to unassemble a bit and recreate code just to adjust things, but that's the gist of it. We went the other way from the binary or the input file back into the database. A quick recap what we've done so far today in this video. We learned how to patch using the UI, how to patch programmatically with the built-in functionality. We learned how the actual assemble function works by sending an EV assemble event to the processor module. And then we covered a better assembler, which is the Keystone engine, and also a plugin for IDA that let us do graphical patching. Then we covered how to actually generate a diff file, how to apply it outside IDA, and also how to apply patches inside IDA. And we learned how to undo patches within IDA in the patch byte window. We concluded by simply patching a binary file and reloading it back into IDA. So I think this covers all the methods we can patch with IDA. Patch, which includes also assembling. Of course, there are other ways. There are so many APIs in IDA, but this is a good way to start with patching if you need to patch your database. Okay, so I hope you found this video useful, and I'll see you next time. Thank you.